Third and final lecture on Chapter 6. In Chapter 6, we've been talking about the second law of thermodynamics and some theoretical maximums for the amount of energy that we can get out of a heat engine, and also theoretical maximums of the performance that we can get out of a heat pump or a refrigerator. And what we have learned to this point is that we can never get 100% of the heat from a heat engine to be converted into work or power, because we always have to eject heat or exhaust heat out to the environment. Now, if you think about this, the work that we get then is going to equal QH minus QL, unless we have parasitic losses. But theoretically, in a perfect world, this is what we would get. So as we reduce QL, we increase the work that we can get out. And therefore, we increase the thermal efficiency of the cycle. Now, what we're going to talk about today then is what is the theoretical limit. Since we know that the theoretical limit is less than 100%, what is the theoretical limit? Well, there are two ideas that I kind of want to entertain. One, of course, is that we're not going to have any parasitic losses. In other words, we're not losing any of the energy to the system itself, which means that the cycle would be reversible. Another thing that we find is that we always lose energy on any heat rejection cycle, which we're going to study more in Chapter 7, on any heat rejection or heat acceptance cycle. But we would want QL to be as low as possible. So how do we make QL as low as possible? Well, let's think about another idea. Let's say that we have this reversible cycle. There's nothing going on mechanically that's causing any of our QH to becoming anything but work. All right, but we have Q sub L. Q sub L is expelled to the environment. So in other words, in a car engine, this is expelled to the atmosphere. If you have a furnace running in a building, you're expelling it to the outdoor temperature and so forth. So it's expelled to the environment or to the ambient. And basically, if you think about it, if you have a larger delta T, in other words, if the temperature change between T sub H, where you get your heat, and T sub L, or low, where you expel your heat, the greater that is, the greater amount of work that you have. And one way to think about this is, let's just say, for example, the temperature, the low temperature reservoir outside is at 70 degrees Fahrenheit. Okay? Well, if you had the opportunity to run an engine off of a 70 degree Fahrenheit reservoir and expel it to, say, a 0 degree Fahrenheit reservoir, what that means is that you have some amount of work that could be done between 70 and 0 degrees. Now, later on, we're going to quantify this a little bit more, but one of the terms for this idea is lost work. Now, this is very theoretical because we cannot drop the temperature of the ambient. It's just not possible. However, whatever temperature we're at the ambient, if it's above anything, if there's a temperature that's above actually absolute zero, which is the theoretical minimum, there's some heat that we cannot recover, there's some work that we cannot recover, due simply to the fact that we're expelling to an environment that's at a temperature greater than absolute zero. So this is one place that we lose work, and there's nothing that we can do about that. So it's not really lost, but this is not in our control. because the temperature of the environment is what the temperature of the environment is. Now, another place that this happens, if any of you have ever had a car with a turbocharger, or if you've ever taken a car, just any car from, say, Powell, Wyoming to sea level. If you ever had an opportunity to drive somewhere where we have higher atmospheric pressure, automobiles function better at higher pressure at lower elevations, and that's actually what a turbocharger does. It actually sort of, well, you can never get totally to sea level, but it creates a situation where you're using your exhaust in a way that it's increasing the efficiency of the engine, similar to what happens if you have a higher atmospheric pressure. So all of those ideas are lost work. So there's some theoretical minimum that is based on what the atmosphere is, since we can't change that, of work that we're going to lose. So the theoretical limit would be that it would be a totally reversible engine, that Q sub L would be as low as possible, and finally, that heat acceptance and heat rejection occur in a, now let's put it this way, are complete on T sub H and T sub L. In other words, you're not leaking any heat or gaining any heat in the engine. It's all coming in here, and it's all going out here. All right, so this type of a cycle, the theoretical gold standard, of performance between a particular T sub H and T sub L. In other words, so I didn't even really talk about this, but just like I said, if we could lower T sub L, we would get more efficiency. Also, if we could increase T sub H, we could increase our efficiency. But between a given T sub H and T sub L, there's going to be a theoretical maximum, which is this reversible cycle. And we call this cycle a Carnot cycle. Carnot is the name of a French engineer who developed this idea by asking the question, essentially, if we can't get 100% of Q sub H, if that is not even really a theoretical limit, if that's above our theoretical limit, what is our theoretical limit? And then instead of comparing our actual performance to 100%, which is totally artificial, we could compare it to the performance of the maximum efficient engine, or a Carnot cycle. So it turns out that there's a very important relationship that for a reversible cycle, which of course is theoretical in and of itself, that if you take Q sub H and divide it by Q sub L, this proportion, for a reversible cycle only, is going to equal the ratio of T sub H over T sub L. Now, obviously, this is not true for a non-reversible cycle, and I'm actually introducing it without proof. But in order to do this, you have to report T sub H and T sub L as absolute temperatures. So in other words, as degrees Kelvin or degrees Rankine, not degrees centigrade or degrees Fahrenheit. Okay? But what it means is there's a theoretical and a practical meaning to the idea of absolute zero. So in other words, on an absolute scale, 0 degrees Kelvin, 0 degrees Rankine equals absolute zero. And the meaning of absolute zero, we've never really achieved absolute zero, but we can approach it asymptotically. So we know what the value is. It's about negative 273 degrees Celsius or centigrade and about negative 469 Fahrenheit. But what it means is that the entropy of a perfect crystalline form of matter at absolute zero is a minimum. So it doesn't really make any sense yet. It doesn't really make any sense in the vernacular. But what you can take away from it is that 0 degrees Kelvin, 0 degrees Rankine, absolute zero is an asymptotically approachable minimum temperature. So if you listen to science fiction, sometimes they'll say like all molecular energy stops at absolute zero. That's not entirely true, but it is at a minimum. So if we take a temperature, and this is 0, and this is just greater than 0, and through some means, whatever we're measuring, energy or whatever, we wish to approach this, what we get is something like this, okay? So in other words, the closer you get to absolute zero, the lower your energy is, but it's not a linear relationship. So for our purposes, this is an important relationship. Works only for reversible cycles, which the Carnot cycle is. And we can just say absolute zero is a theoretical minimum. And then what it's a minimum of is a little bit more sophisticated. But all you can say is that it appears that we are not able to go below absolute zero. And here's one just kind of a little thought experiment. In general, how do you decrease the temperature of something? Like if you have ice and you want it to, or if you have water and you want it to freeze into ice, you expose it to a lower temperature, right? So that heat flows out. Well, if we can't go below absolute zero, how can we get below absolute zero to make something absolute zero? So it's sort of a catch-22, sort of a reasoning process. But basically, absolute zero appears to be a theoretical and an actual empirical minimum. All right, so a Carnot cycle then. We can draw a Carnot cycle for a heat engine, and we can draw a Carnot cycle for a heat pump or refrigerator. And we know, and basically a Carnot cycle is a 4-process or 4-stroke cycle where all of the heat is accepted on an isotherm. So in other words, 1 stroke is heat acceptance at constant temperature, which is called isothermal. So in other words, we have Q sub H coming in at T sub H. The 3rd stroke down here is where we lose Q sub L at T sub L. And so the 3rd stroke is heat rejection at a constant temperature, which once again is isotherm. And that means we have Q sub L at T sub L. So what happens between here and here and here and here? Well, if I'm going from here to here, I can say that the 2nd is the power stroke, or work out. Temperature high has to move to temperature low, right? Go from here to here. And we can't lose or gain any heat. And the word for that is adiabatic. So in other words, there's no heat lost or gained here. All we do is get work out. And here, on the 4th stroke, we have to go from T sub L back up to T sub H. So in other words, we're changing our temperature back to the original temperature. And there is no heat, once again. And this is also adiabatic. And so this exact cookbook or series of processes is the most efficient engine that we can develop theoretically, and it's called a Carnot cycle. Now, it turns out that any truly reversible cycle, which of course there aren't any, but any theoretical reversible cycle, whether it follows these 4 steps or not, can be viewed as a Carnot cycle, but that's a little esoteric for this point. What I want you to look at here, especially for those of you in mechanical engineering or chemical engineering, because you will do this later on when you take Thermo 2 and when you take heat transfer, this is the way that we define a cycle. There are tons and tons of thermodynamic cycles. In your textbooks, we're not going to cover very much of this in this class, but for those of you in those majors, you'll cover them pretty extensively later on. Beginning with chapter 9 in your textbook, there are several chapters that are devoted to different types of thermodynamic cycles. And you can learn them, like you can memorize them, or you can say, well, an Otto cycle looks like this, a Stirling cycle looks like this, a gas vapor refrigeration cycle looks like this. Or you can just think about analyzing them based on the processes involved, because they all have these things in common. A power cycle or a work engine, the purpose of that is to create work or power. If it's a refrigeration cycle or a heat pump, the purpose is to move heat in the opposite direction to how it would normally move. So whatever the cycle is, there's going to have, most of them are 4-process ones that we study. Some of them are two-process cycles, 2-stroke cycles. You can have multiple strokes, but 4 is pretty common. And you can always analyze them based on whether the strokes are polytropic, isothermal, adiabatic, isobaric, or whatever. So, but if you look at any cycle and you break it down by the processes, then you're going to be able to analyze the cycle. So this is the only cycle that we're really going to do in this class, but I'm kind of, so in other words, we're going to talk about this as an isolated cycle because of its theoretical importance, but for those of you going into, those of you that will be taking Thermo 2, or heat transfer or anything like this, this will be, or power cycles, power engines, all kinds of machining things, you'll be exposed to this later on. So maybe you'll go, oh, I remember. She said, don't, you know, you don't have to look at them separately. They all kind of have to be analyzed in the same way. All right. So Carnot cycle are these four processes, starting at T sub H and ending up at Q sub H, the purpose of which is to get out work. Now, a Carnot cycle for a heat pump, or a refrigerator, looks like this. Instead of accepting heat at Q sub H, we reject heat at T sub H. We accept heat at T sub L, and in order to make that cycle run, we put work in. So strokes are the same. This is isothermal, adiabatic, isothermal, adiabatic. Heat rejection in this case, work in this case, heat acceptance, and then just a return to the original temperature. So, for a reversible cycle, what this does for us is it gives us a theoretical limit. What is, then, the theoretical limit of efficiency and the theoretical limit of coefficient of performance for both a refrigerator and a heat pump? Well, it's always, for anything, the thermal efficiency is going to be the work we get out over the heat we put in, which is, of course, Q sub H minus Q sub L over Q sub H, which is, if I divide everything by Q sub H, 1 minus Q sub L over Q sub H over 1. So I don't even have to do that. I could just put it like that. Okay? But now for a Carnot cycle only, because I introduced, sort of without proof, the idea that for a reversible cycle, we have this relationship where the ratio of the heats are the same as the ratio of the absolute temperatures. I can substitute temperatures here, and I'll get the efficiency of a Carnot cycle. So these are both true for a Carnot cycle or for a reversible cycle. For a real cycle, only this is true. So, in other words, you can compute one or the other for a Carnot cycle and compare it to a real cycle and come up with a Carnot efficiency. Now, the other thing I'll notice, I would like you to notice, I've already noticed it, but if you look at the thermal efficiency of a Carnot cycle, how would you make this equal to 1? In other words, how could I have a Carnot efficiency equal to 100%? If it's 1 minus T sub L over T, say it? Yes, if T sub L were equal to 0. If T sub L equals 0, then Carnot efficiency is equal to 1, which is 100%. So that means if we are rejecting heat to absolute 0, then we would have a 100% efficient Carnot cycle, which goes back to that idea of lost work. Anytime the opposite or the reverse is, if we have the converse of that, if we have 100% efficiency rejecting to absolute 0, it implies that if we're not rejecting to absolute 0, that we're going to have less than 100% efficiency. Okay? And we can say that verbally, we can also say it mathematically. Because anytime T sub L is not equal to 0, this ratio is not going to be equal to 0, and so this difference will not be equal to 1. All right, what about coefficient of performance? Well, the coefficient of performance for a refrigerator operating in a Carnot cycle is always, just like we said, it's what we're after, which is Q sub L over W, Q sub L over Q sub H minus Q sub L. And if I divide everything by 1, I get 1 over Q sub H over Q sub L minus 1. All right, and for a heat pump, we're not after Q sub L, we're after Q sub H. Same idea. Except for here, we would get 1 over 1 minus Q sub L over Q sub H. All right? So we just have these different, these are the same equations as we came up with before. But like I had said, Q sub H over Q sub L for a reversible cycle is in the same proportions as T sub L and T sub H. So this is also equal to 1 over T sub H over T sub L minus 1. And this is also equal to 1 over 1 minus T sub L over T sub H. And once again, there's no, the theoretical limit of a coefficient of performance is infinity. There's really no limit on that because once again, all we're talking about is moving heat. We're not really even changing forms. We're just pumping heat from one side to the other. Okay, but for coefficient or for thermal efficiency, we have this. Now, it's very tempting when you start working problems to say, oh, here Astrid wrote this equation that says the thermal efficiency is equal to 1 minus T sub L over T sub H. When is that only true? For a, yes, a Carnot or any reversible cycle, but it's not in general true. In general, the thermal efficiencies involving heat are true. They're true for both reversible and irreversible cycles, or reversible and real cycles. The temperature ratios are only true for reversible cycles. They represent the theoretical max. All right. So shall we work a couple problems? There's also a little corollary here that we've talked about. There are different types of perpetual motion machines. And they have in common one thing. What do you think that is? They don't work. Okay? So there are different types. There's a perpetual motion machine of the first kind, which means that there's no friction. Well, it means that energy The first law of thermodynamics is that energy is conserved. The perpetual motion machine of the first kind is energy is created in a process. Perpetual motion machine of the second kind violates the second law of thermodynamics, which we've begun talking about, but basically no entropy, which is a quantity that we'll talk about later. Entropy is not lost, or not, does not change, let's put it that way, which we'll describe what that means later. And then there's also a perpetual motion machine of the third kind, which is one that doesn't have friction. So the answer is none of them work. So I always draw some things, a couple of which I can draw. But this is a perpetual motion machine. This is my idea of what the Easter Bunny looks like. And how about Santa Claus? So what do they all have in common? They're not real. That's exactly right. So you can think about that when you talk about perpetual motion machines. Okay. All right. I saw somebody on Facebook this morning made an Easter bunny out of a fried egg and pieces of bacon. So maybe I should do that and take a picture of it for posterity, because my drawings are pretty much lacking. All right, so let's do a couple of problems. What are we going to use? How are we going to use this? Okay, I'm going to look, let's see, at some problems for Carnot cycle. I'm going to come back over here just to the PC. All right, and take a look at what we have for problems for chapter 6, because I do not wish to do one of your homework problems, but I want to get in the ballpark. We have Carnot heat engines go from problem 72 up through 83, and I've assigned 77 to you, which is an excellent problem. So I'm going to do problem 676, and we'll use the same principles that 77 uses. So you have to pull into this the ideas of what you know about thermal efficiency, what you know about the relationships between heat and work for a heat engine, and the ideas of thermal efficiencies, which are the same ideas that you'll have to use for problem 677. So 676 tells me that we are talking about a Carnot cycle, and it is a heat engine. It says it receives 650 kilojoules. That is going to be, since it's receiving, that's Q sub H, right? Heat from a source of unknown temperature. We don't know what it is. And it rejects heat, that's Q sub L, in the amount of 250 kilojoules to a sink, which is, they usually call this a source and this a sink, which they're both just heat reservoirs, at 24 degrees centigrade, which we know already for Carnot we're not going to use centigrade, we're going to use kelvins. So we add 273, and that turns out to be 297 kelvins. All right, it asks us to determine the temperature of the source, which is T sub H, and the thermal efficiency of this heat engine. Well, it is a Carnot cycle, so we can use both equations. Since it's Carnot, and since it is a heat engine, we can use this equation, and we can use this equation, right? So we know that the Carnot efficiency is equal to 1 minus Q sub L over Q sub H, and because it's a Carnot, it's also equal to T sub L over T sub 1 minus T sub L over T sub H. Right. Well, if I look at this Carnot efficiency, I should put a question mark here because I'm looking for that. I know that it's equal to this. I have Q sub L and I have Q sub H, and they're both in the same units, aren't they? So that means that the units will cancel out. I get 1 minus 250 over 650, both in kilojoules. And if I do that math, I take 250, divide it by 650, and subtract that number from 1. I get that my thermal efficiency is 0.6154. Or I could say that it's equal to 61.54%. Now, how can I find T sub H? Well, the answer is I have T sub L. I can use this to solve for T sub H because I have my thermal efficiency. 0.6154 equals 1 minus T sub L over T sub H. Or if I take that number and I pull 1 over to this side, I get negative 0.3846 equals negative this, or I can just multiply through by negative 1. I don't have T sub H, but I do have T sub L. So I can cross multiply, or in other words, this times this is equal to this times this. So I can say T sub L equals 0.3846 times T sub H, or T sub H equals T sub L divided by 0.343846. T sub L, I have to report that in kelvins or else the proportions are not correct. 297 kelvins over dimensionless 0.3846 equals T sub H. So if I do that math, I get 297, 772 kelvins. And I could subtract 273 from that to report it in degrees Celsius, 499 degrees Celsius. Do you have any questions about that? No? It's pretty straightforward. Once you start to run the numbers, it's not easy, I will never say that, but it's more or less straightforward. So the next one I'd like to do is a Carnot heat pump or refrigerator. Maybe we could use one in English units. Okay, let's take a look at number 699E. Gentlemen, happy Easter, and this will be posted on Noodle, so you'll be ready to go. All right, have a great. Oh yeah, thank you, and have a good long weekend. Thanks. See you guys. Happy. That's it. Exactly. All right. So 699E says an air conditioning system is used to maintain a house at 72 degrees Fahrenheit. That's my T sub L. When the temperature outside is 90 degrees Fahrenheit. If this air conditioning system draws, so my W dot, 5 horsepower, I know it's dot because horsepower is a rate, correct? Determine the maximum rate of heat removal. So what I'm looking for is Q sub L dot max equals what? All right. Well, first of all, anytime you see max, what do you think it is we're talking about? What kind of a cycle? Start writing it out. C A Carnot, thank you. So maximum is code word for Carnot. So what we're doing is we're saying this is a Carnot cycle. We're sucking heat out of the house and pushing it into the ambient outside, and we're doing so by using a 5 horsepower compressor, taking 5 horsepower of power going in. Now obviously we're going to remove heat less efficiently than a Carnot cycle, but we're talking about what is the max. All right. So we know that coefficient of performance for a refrigerator or air conditioner max, which is Carnot, is going to equal what we are trying to get out of this, Q sub L. In this case, we're talking about rates, which is no problem, over the power that we have to put in. And we also know that Q sub L dot, the work W dot is going to equal Q sub H dot minus Q sub L dot. All right? Now we further know that for a Carnot cycle, we can substitute the values of temperature for our heats. So we can say T sub L over T sub H minus T sub L, and that will be our maximum Carnot efficiency. Okay, now we can't use degrees Fahrenheit because that is not an absolute scale, but we can say degrees Rankine is equal to degrees Fahrenheit plus, is it 459 or 469? Do you guys know? I know. I always think it's 469, but then I think, wait a second, maybe it's not. All right, hang on just a second. Let's find out. So the principle would be the same, but degrees Rankine to Fahrenheit. There you go. The number is 459. Okay? All right. No, I did it right the first time. Sorry. 459 plus degrees Fahrenheit equals Rankine. That's not correct. I've got that backward. I know what I'm saying, but I'm doing it backward. So if we have, let's see, for example, 90 degrees Fahrenheit there we go. Yeah. So the number, the Rankine number, is a bigger number, which of course makes sense. Okay, so if we have 90 degrees Fahrenheit, this is 550 roughly degrees Rankine, and 72 is 532. Okay. So we have to make sure to use the Rankine scale, being as that's our absolute scale. So what that means is that we can take our T sub L, which is 532, and divide it by 550 minus 532. And this number is just the difference between this, but that's okay. Let's go ahead and 532 divided by 18. So our coefficient of performance for this refrigerator operating in a Carnot cycle is 29.55. So that's a huge number, but you expect it to be a huge number because it's a theoretical maximum. And as I said last time, thermal efficiency has to be 1 or less. There is no real upper limit to, there's no number limit to coefficient of performance because we are not changing energy forms, we're just pushing energy from one side of the cycle to the other. So very often a real refrigerator will have a coefficient of performance of 7 or something like that. So it's not the same as coefficient of as thermal efficiency. Okay, so air conditioner system is used to do this. If the air conditioner draws this, determine the maximum rate of heat removal. So what we are looking for, the maximum rate of heat removal is this value. All right, so let's go back to this original equation, and we can say We also know that the coefficient of performance, we know that the value is 29.55. We also know that that's equal to the rate of heat removal divided by the work that we put in, which is 5 horsepower. So we can use this equation to solve for Q sub L, and we get 29.55 times 5 horsepower. And in units of horsepower, which is not a great unit, we can take 29.55 and multiply that by the horsepower, and we get 147.78 horsepower. All right, now rate of heat removal. Heat is often measured in BTUs, so a rate of heat removal could be in BTUs per second, and a BTU is 778 foot-pounds of force. So we could convert it into this and into BTUs per second. This answer is correct, it's just that horsepower is not usually used for rate of heat removal. So let's go ahead and take our number, 147.78 horsepower, and multiply that by, we know that 1 horsepower is the same as 550 foot-pounds of force per second. And then we further know that 778 foot-pounds of force is equal to 1 BTU. So we would cancel those, and we get BTU per second after we take that number multiplied by 550 and divide it by 778. And we get a rate of heat removal then of 104.5 BTUs per second. All right. Now on a test, I would tell you what units. I wouldn't necessarily expect you to know that a horsepower, I mean, you can kind of think about it, why, you know, horsepower measures power, right? So measuring heat removal in units of power, they're dimensionally equivalent, but it's just a little odd. But if I wanted it in a different unit, I would specify that, okay? All right, do you guys have any questions about chapter 6? All right then. So I will, the homework is posted. We are ready to go. This is the last video for chapter 6. So when we come back after the Easter holiday, we will ask questions about chapter 5 and 6. You will have turned in your chapter 5 homework at that time, and we'll begin chapter 7. So have a great break, and we'll see you Tuesday.